Good morning students. Today we are going to discuss in this video about the inorganic reaction mechanisms. In our previous videos we have discussed in detail about the lability and inertness of the complexes. Now let's discuss how this lability leads to the reactions and the mechanism involved in inorganic reactions. By far you might have discussed in detail the reaction mechanism in organic compounds. Now let's see the preview in the inorganic complexes, how it goes for. So let's first discuss the free energy diagram, where the free energy and the extent of reaction are plotted on y-axis and x-axis respectively. And we can say, when suppose a complex mx combines with the incoming ligand y, and it reacts with and replaces y, it replaces x, and results in formation of my as a product and x as a leaving group. So we can plot the energy profile diagram that the reactant is lying at this energy level, and then it passes through a transition state and it goes to the products. The products are obviously at a lower energy than the reactant, and this is called the free energy change, that is delta G hash. And this is, at this point, this is the activation, this is the amount of activation energy which anybody needs, and the threshold level when it crosses and results in formation of the product. So obviously the product has to have little less energy than the reactant to take place. So this is the simple energy profile diagram which you might have discussed and seen several times before. Now let's discuss the types of reactions, inorganic reactions, which are possible. There are major three types of reactions which are possible: the substitution reactions, redox reactions, and ligand type of reactions. Substitution reaction means the metal has a ligand, suppose mx, and the y comes and reacts with it to forms my. So the x is being substituted by y directly. That means it's a substitution reaction where the bond between m and x gets broken, and it results in formation of my complex. Okay. The other one is the redox type of reaction, where the electron transfer takes place. These are also called as electron transfer reactions, where the electron is being transferred either from the ligand to the metal ion or to the metal to the from the metal to ligand. And the third one is the ligand reaction, where the metal ligand bond remains intact, but the ligand itself undergoes some substitution reaction, and all the reactions takes place on the ligand. The bond is not getting affected, and the ligand forms some type of isomer or some other substitution. This happens when the ligand size is quite big. So we are going to go step by step and discuss the types of reactions. First we are going to do the substitution reaction discussion with respect to octahedral complexes, and then with respect to square planar complexes. Why we are discussing the substitution reaction in first? Because these are the major type of reactions which are shown by the transition metal ions. Okay. Now let's discuss the ligand substitution reaction in octahedral complexes. Substitution reaction, a general substitution reaction, can be written like this: mxn, this is n, not h, okay, just write it n, mxny plus z, which gives you mxnz plus y, where m is the metal ion, xn is, which is not undergoing any substitution, these are the ligands which are left during the substitution, y is the leaving group, and z is the entering group which is going to react. Now n will be 5 for octahedral complexes, because obviously we know an octahedral is mx6, where we have taken mx5, and y, which one will leave. Okay, we are going to mention all the time. It's not that the y and x has to be different, which is the leaving group. Now we are going to discuss the substitution reaction, which can be of two types, as you have seen in organic chemistry also: electrophilic substitution and nucleophilic substitution. Electrophilic substitution means obviously the electrophile attacks the metal atom, and the nucleophilic substitution is the nucleophile attacks the metal atom. Obviously the nucleophilic substitution is much more common because metal center is always most of the time positively charged. So we can consider the attack by the nucleophiles such as chloride, OH-, cyanide, or other ligands which are negatively charged. Now in these cases, there are few different type of reactions like acid hydrolysis, base hydrolysis, anation type of reaction. Now what is acid hydrolysis? Obviously the Z, which is the attacking group, is H plus ion. When we are talking about base hydrolysis, Z is OH minus ion. And when we are talking anation type of reaction, that is anion is getting added, then it is Z is an particular anion when we are talking. Here it is anion, here it is cation, similarly here it is only the anion. Now we are talking about anion other than hydroxyl, obviously, like SCN minus or cyanide or other negatively charged anions. Now, two types of mechanisms are proposed for this, SN1 and SN2. We are going to discuss the similar things which you have seen in organic reactions, so it will be pretty easy for you to understand. SN1 type of reaction and SN2 type of reaction. The SN1 is also called as dissociative type of reaction mechanism, and SN2 is all known as associative type of reaction mechanism. We are going to come back to this dissociative and associative later on. First, let's discuss what is SN1 and SN2. SN1 is, S stands for substitution, nucleophilic unimolecular reaction. You remember according to the kinetics, what is unimolecular reaction? Which depends on, the rate depends on only one compound. So it occurs in two steps, that in octahedral complexes, that MX5, the first step is the MX5 gets broken into two parts, MX5 and Y, where MX5 is the intermediate, quite stable. So if we want to draw the energy profile diagram for it, so how the energy profile diagram goes? It goes like this. This is the intermediate, that is MX5. Here the reactant, then the intermediate stays for some time, it is stable, and obviously it can be separated if in case it is much more stable. Then again it crosses one more energy, activation energy, and it gives us a product. Okay. Now the 5 coordinated intermediate activated complex which is formed, this is the 5 coordinated, as we can say MX5. It can be either square pyramidal or trigonal pyramidal shape. It can have two shapes, either square pyramidal or trigonal pyramidal shape. Now in the second step, what happens? The nucleophile attacks the MX5 and it forms MX5Z. This is the fastest step and this is the rate determining step, as it used to happen for the SN1 mechanism. So the first step is the slowest step and the rate determining step, that is the formation of the transition state, and the second step is the fast step and leads to the formation of a complex which is having a coordination number of 6. I think I am quite clear. Now let's discuss the mechanism involved and the overall reaction. The MX5, which is the slowest step, the Y goes out and then the Z comes in and forms MX5Z complex. Now this is the octahedral complex which is being shown. There are two possibilities as we discussed, trigonal bipyramidal intermediate or square pyramidal intermediate. We can make both the shapes, and again it undergoes the reaction which is the fastest reaction and it leads to the formation of octahedral complex. I think this diagram is quite clear. Whenever you are asked to discuss about the reaction mechanism, explain it using a pictorial diagram. It becomes much more easy and more convincing. Okay, now this is about SN1 type of reaction. Let's discuss the SN2. Now in SN2, as we have seen before, this is MX5Y, which is the slowest step, and in the same step only it consists of like let's discuss first the substitution nucleophilic bimolecular reaction. Obviously bimolecular means it depends on the two reactants and it is a single step reaction. It doesn't get split into two parts. That is it just goes to the formation of an transition state. It goes from the formation of transition state. No intermediate can be separated. Now how the transition state is formed? MX5Y is being attacked by Z, and then a complex is formed which is MX5Z. This is a coordination number with 7. It has coordination number 7. This is the transition state which is quite unstable and which finally declubs and forms MX5Z. Now, so the incoming nucleophile Z attaches MX5Y to form 7 coordination unstable transition state, and the rate is given by K2 equals to MX5YZ. I hope I am quite clear in this. Let's discuss the mechanism for it, the structural mechanism, that mx5y we have, and then the slowest step, which is the rate determining step as well, and we have 1, 2, 3, 4, 5, 6 and 7. I think I have not drawn this one. Okay, so now here we are having mx z, and here it is y. Okay, so this is a 7 coordination complex which is formed as a transition state, and then in a very fast step, in the last step, the y comes out, and again we get a coordination complex of 6. So this is a simple mechanism for SN2. Now we can discuss, going back, what do you mean by the dissociative and associative type of complexes. Now dissociative means, as you saw the mechanism, dissociative means the metal ligand bond is being broken and the Ml6 is going to Ml5 in between during the reaction. This is called as dissociative mechanism, where the metal ligand bond is broken. In associative type, in the same complex, one more ligand is being added, and we are getting from coordination number 6 to coordination number 7 complex. So that is called as associative type. Now the associative type of mechanism is favored in case the reactants are having lower coordination complexes. When we have lower coordination complexes, the associative mechanism is favored, and the rate also depends on the entering group. Okay, so the associative mechanism is favored by the entering group, because the entering group goes and combines and forms a 7 coordination complex. So it depends upon the entering group, and the lower coordination complexes only favors associative mechanism. The dissociative mechanism is favored majorly by octahedral complexes and the smaller metal clusters, and the rate depends on the leaving group. Why this happens by the smaller metal clusters and octahedral complexes? Because easily they undergo the metal ligand bond cleavage. Okay, now let's discuss in brief the comparison between SN1 and SN2. In SN1, obviously the rate determining step is Ml bond breaking. In SN2, the rate determining step is mx5 to mx5yz. The SN1 is a first order reaction, SN2 is a second order reaction. SN1 undergoes preferably through dissociative mechanism, and SN2 undergoes preferably through associative mechanism. I think that's all for the reaction mechanism. In the next lecture, we are going to discuss about the square planar reaction mechanism, the reaction mechanism involved in square planar complexes, and then further the electron transfer reaction mechanism. Thank you.